All right, hello everyone. Welcome back to Hidden Gems, the second part. So again, this is a session where we try to look at some tips and tricks for underutilized capabilities in Solid Edge. And in this second session, Sam will be looking at inter-part relationships. And then after him, Kevin from Siemens again will be looking at model-based design practices and how they can be used in Solid Edge. So at this point, I'll pass on over to Sam for his presentation.
So interpart relationship or interpart associativity inside of Solid Edge, it's something that's been around for a good long while. And it helps you create and design your products with help and context of another part or another assembly. So kind of depending on how you want to include, the geometry, you can make it associative, kind of what we're going to be concentrating on. You can make it non-associative. So in other words, you use it once and you forget it. Or you can actually have one part drive another within the context of a part or within the context of an assembly. I like it where the way I'm going to show it is where, you have an assembly and you're doing a top-down, a sort of a top-down type of design work. And if I want one piece, one part to say I go and edit it, make changes to it, the other part actually updates with it. So outside of using variable tables or other forms of kind of linking the part, we're going to go and try to use inter-part relationships to kind of drive that associativity between the two parts. So let's see here. Let me get rid of my little window here. Okay. And loading in on there's a, oh, I've got it's kind of one of our data sets, but I think it's a part of an engine, like a lawnmower type of chassis. And then I've got an engine here that I kind of want to go ahead and I've got on a mounting bracket, and I want to mount that mounting bracket onto my chassis now. The engine's got some holes drilled in it. I mean, the motor mount for the engine has some drills in it for the engine, but I need some holes over here for the actual motor mount to attach to the chassis. Now I can use an assembly feature. So in this particular assembly feature, what I'm going to do is I'm going to drive these cutouts into the from the part going into the actual chassis. And of course, when you're dealing with ordered, you can orient your plane by using your toggle buttons down at the bottom. So I want to choose this as my bottom left-hand corner, have the view automatically orient over here. And I'm going to go ahead and kind of design my bolt holes kind of where I need them to go. And this is just basic sketch operations that we're used to. So very first thing is sketch it, then I relate it. It kind of takes some of the extra steps out that you would use in, say, dimensioning and otherwise. So made the two equal, and I'm going to go link the two with a construction line here. Hey Carter, your mic's not muted.
Thank you.
Okay, so going on from there, I connect the two, and then of course, throw my horizontal vertical in there and make them aligned with each other, and then go ahead and grab a center point, start dimensioning out, give it some more definition now. So in between dimension holes, I can play around with that a little later. And if I want to do from edge to the center of the hole, and right now I can't click on the edge because one of the important things to kind of consider and keep in mind is if a part's not activated within the assembly, you can't select any of the components on it. So keep an eye on your assembly tree to see what's active and what's not active. Here I can go ahead and position the holes from the edge, lock down that driving dimension there, and then I need those two holes. Go ahead and see, I only dimension one since the other one's equal to itself. But the other thing I need to do is make sure that this is centered up over here. So use my horizontal vertical, good placement of the holes. Now I need those holes on the opposite side too as well. So I can mirror it beforehand, but I'm going to go ahead and mirror it using inside the sketch. So as long as I have a good plane or a good orientation spot that I can go to, I can mirror the entire selection over. And it doesn't quite show up over here because it's an assembly and it doesn't like video recording software or video webinar, things like that. I found that. So there is a bounding box around there, take my word for it. I click and hold down and I'm selecting both of those. Okay, and then specify my axis, and that's going to be my center point axis. I want to mirror about that. Plug those holes over to the other side. So now that I've got my mounting hole sketches, I can go ahead and place the feature. And again, this feature, the cut that I'm going to be performing, not only is it going to go through the mounting plate for the engine, but it's also going to go ahead and place that same hole pattern on the chassis itself. So tell it which two I want to go through, accept it. Always right click to accept or hit the check mark. And it'll go ahead and drive those through and place those actual holes on each one of those part components. So if I take a look, hide the motor mount, I can see that the holes are in the chassis as well as the motor mount plate. So we'll go ahead and save our work right quick. And then we'll go ahead and tear it. Let's take a look and see what happens, because right now there's no associativity between this hole here and the one in the chassis. So besides design intent, if we had design intent turned on, it could possibly it's picking up the other hole on the opposite side, but it's not really picking up the hole on the bottom on the chassis because right now they're not really, they're not associative yet. But I do want them to be associated because I want one to update the other. So we'll undo that change right quick, and we'll take a look at I think I'm opening up the actual pan itself, and you can see that it's just, right now it just consists of a couple of tabs. There's my cutout. My cutout got placed into synchronous, but the same thing here. If I make the change on the plate, it's not going to, even within the context of an assembly or context of a part, it's only design intent is only picking up the opposite side of the actual, the other component inside the actual motor, the mounting bracket, but nothing connecting it to the actual chassis itself. So to create that relationship over here at the top, over here in the home, there is a command. So we got inner part copy, inner part assembly copy, and create inner part relationship. Okay, and it's going to ask me two questions: who's going to be the driver, or what's going to be driven? Parent-child relationship, and who's going to be doing the driving? Who's the parent? Who's the child? So the child then would be the motor mount bracket, and the driving one I'm going to make the chassis. So if I adjust the chassis, the motor mount adjusts as well. When I pick that solid edge, will automatically go and look for relationships that it can go ahead and attach. These are the relationships creating the associativity between part A and part B. Part A being the chassis frame, part B being the motor mount. So I found cylindrical, concentric relationships on my cylinders and equal radiuses. And I also found a coplanar there, so it's anything that's associated. I'm gonna go ahead and save and accept all the changes that it made. And you can see there's a link now that's a part of my motor mount. And if I edit that part in place, show you there is now some surfacing. There are some surfaces now that are connecting my chassis over to my part. Now these are just inner part copies, but these inner part copies are special because there's the glue or there's a chain link that are connecting my two parts together. So if I go back to the assembly side, and since the chassis part is going to be my driver, and it's going to determine where the holes are located on the actual motor mount, I can go ahead and choose just the hole. So again, if control space bar on the assembly side to go from part priority to face priority, I can go ahead and adjust those holes just on the chassis itself, whether in the chassis part or here in the assembly side. Either one, it doesn't matter. If I update that and then display my motor mount over here, you can see that the holes automatically filtered on through. They automatically updated. So now I have some intelligence. I have some automation that's built into the system here. Okay. If I undo it, go back, I can go to the opposite side, and instead of picking that hole, let me pick this hole over here. And design intent, my little AI sitting back in the background, he's guessing, he's picking up the coplanar aligned holes between this side and the other side. So again, I only have to edit once, and the motor mount automatically adjusts, going with me. So in the assembly side, I can create inner part relationships between two component pieces and have one drive the other and make editing and making changes, you know, a little more easier to do. I can't change the actual component piece over here because this is, remember, parent-child relationship. As long as I have that purple surface and that link placed in there, these two guys are permanent. Now I can go ahead and take it out if I wanted to, but as long as those two guys are linked, I have that associativity between the two parts. Okay, another example that we can take a look at is something that's been part of the software since I think about ST6. So here I've got a base plate and a little hydraulic motor, okay? And one of the tools that we have, you can see that the base plate doesn't have any information that, you know, to seed this motor correctly. So one of the things we can do besides, you know, trying to get this motor to fit on this plate and to get the necessary, you know, in order to get it fit flush, the motor has two faces on it. It's got the shaft and it's got the seating mount for the other component. And what I can do is I can use Boolean subtract. Okay, so I can use one body to take out, acts like a tool, one body to remove certain features from another body. So one acts like a tool body, the other one acts like the tool base, and I can go ahead and quickly transfer that data from one model to the other. So in this case, I've got the two cutouts, you know, one for the shaft, one for the clearance of the front end of the motor, plus the mounting holes. The only drawback from just doing this from the part side is that if I go back to the assembly and say you know, this motor changes or the faces, somehow the bolt centers have to move. There's no associativity between this and the actual part component if you just use the Boolean subtract there on the part side. Okay, luckily there's some extra components that have been added in to Teamcenter, I mean not to Teamcenter, Solid Edge that allow us to, you know, create some of that associativity. So you saw me do the subtraction there on the actual part level. If I stay here on the assembly side, now I can use subtract, and it's going to be over here on the top side. And I can run the same command, but you see I got a couple of extra options. I can create synchronous options to recognize holes, exclude holes. So I have a little more options, a little more control than what I had on the part side. But using the synchronous side still doesn't allow me the flexibility of creating associativity. So again, if I hide the main motor, you can see that I've got the two holes plus the four bolt holes. Now you notice that the level that's excluded would be the bigger hole, and that's because that option was turned down a little too low. But mainly my main concern is the bolt holes over here. They're not associative. Okay, they're not following through. So with going back in and undoing that, going back to the same command over here, see, I got do not recognize holes larger than 170 millimeters. I could probably jack that up in order to get the other one. But if I maintain the links for ordered operations, that bottom section down there, the bottom option, I can run the same command again. But this time, I can create associativity between the motor and the base plate. And as soon as I accept the command and get out of it, you see a little chain link now form between the base plate. I now have extra data in there. So if I look at the actual base plate and place activate into it, you will see some inner part copies. And it took the entire thing, which I'm not complaining. It's always good because it got the sides that I need, the sides that count. So if I do the same move again and say change the bottom side of this plate out, I'm going to extend it out, the holes come with it. And if I go back and take a look at the base plate now, let's add and place activate into that one. There we go. You can see that the bolt holes, as I start hiding some of these surface copies or the inner part copies, you'll notice that the bolt holes went along with it. So Control Q toggles off the assembly. But you can see now that the bolt holes of the base plate and the bolt holes of the actual hydraulic motor are fully associative because of the inner part copies of the actual bolts itself in this case. So not just cylindrical cutouts, you know, like we saw in the previous example here, it's the entire, you know, I made an entire physical copy of it. So again, associativity between two components, you know, done automatically, automation. You know, so some of these little tips and tricks, you know, if you're not using them, definitely do come in handy whenever you run into little problem, little issues, but you want to do creative solutions to creative problems. Um, One more, you get a bonus. And this is kind of one that I do at the end of, during training class, training sessions. This is a cool little thing I show the students, but this kind of incorporates synchronous and ordered all within the same model. You don't have to choose one or the other. You can create hybrids, okay? And it's a fun little exercise that, I normally go through. It's just a silly little part, but you know, it does go in and kind of expose people who only use ordered and don't quite, what to do with synchronous. You can blend the two environments together. So here particularly, for instance, I'm starting off a sketch inside synchronous. Okay, later on I'm going to transition over to ordered, but start off with a polygon shape. Pick a base, throw down my sketch. This particular is I'm going to go octagon. I think there you go. Let's go to an octagon. Let's orient it. Give it a size. No particular size needed here, but once I got this sketch, what I can do is I can copy that sketch using my synchronous tools. So synchronous steering wheel isn't just limited to a 3D part. You can also copy sketches, and I don't have to predefine a plane either. The plane is automatically defined once the height and everything is defined by the steering wheel itself. So I can offset two sketches fairly quickly instead of having to offset a plane, go to the plane, create the sketch, project the sketch. Okay, with these two sketches now living inside of synchronous, I can then transition to ordered and finish off my design, or add extra definition to my design. So in this particular case, I want to loft these two pieces together. Okay, so that means that the first part is in synchronous. Synchronous really doesn't care about order, which came first, chicken, egg, as long as there's a model to deal with. When ordered, you're dealing with specific steps in the feature tree. So one has to come right after the other. Well, with these two sketches existing inside of sync, I have the flexibility of using that ordered recipe that ordered is following to recompute at all times. So I can manipulate the sketch independent of the actual the ordered command or the ordered geometry that's sitting over there. So I can twist, I can pull, in this particular instance, I think I'm gonna, as long as I got the steering wheel, and the steering wheel, I can change orientation, so I can change the tilt of the face if need be. And ordered is always going to be there to solve it because it's lofting the two pieces together. It has that command. So as long as I don't break it too much, you know, give it too much heartburn, and still come up with what's it called, a viable solution that ordered can recognize, I can create quick on the edit flies to this particular shape that could probably take me a bit longer inside of ordered, because in ordered I had to go to the sketch, open the sketch, rotate the sketch, then come back and make sure it solved or it didn't solve. So by having the hybrid of the sketches inside of sync and then the final solution inside of ordered, I can come up with different changes to my design. I can play around. My creativity then starts taking over because I'm not just limited to, if I'm going to go ahead and change this design, it's going to take me about 20 minutes to do. So I can push, pull, twist, lift, and then I can even go off into ordered and apply my treatment features. If I wanted to go ahead and put in round my edges, the benefit of doing this inside of, let's see, face, there we go. The benefit of doing this inside of ordered is I can come back and change these and change them en masse versus, in synchronous, you can still change, the radius, but you have to go and pick each individual leader line. Here I can go back, suppress, if need be. So there is a benefit of doing some of these things, especially the end treatment features, the stuff that your design's already done. Now you're just either cleaning up, breaking edges, or making it look nice further on down for utilizing I don't know, your design downstream. So here in this case, I'm gonna go ahead and make a thin wall. I'm gonna hollow the thing out, give it a universal thickness. Okay. Okay, so now I've got a little cup that's still has the synchronous sketches because they still exist, and I still have my steering wheel. And again, I can reorient my steering wheel to a specific point, specific location. As long as I don't get too crazy with the, with the design change, I can stick back and I could say twist this back around the other way. I could twist the face back around. But again, you can get too, you can go overboard and then to start solving just like it is now. It's like, okay, that's too much of a twist. You know how now my rounds got destroyed and my thin wall got destroyed. So you still has to be a viable model. And you can see there, they complete. So Control Z is your best friend here. There's that undo, as long as I don't save, go to another tab. And I think that we have to investigate, as long as I have that undo, I can go back and I can still edit and manipulate that model. But that gives me an extra, an extra layer of freedom per se on my model. So with by having those two simple sketches over here in the synchronous side allows me some freedom and the ability to be a little more creative when I go in and start blending the two environments together. And with that, I will turn it over to Kevin, who will have some other nice tips and tricks for us.
Hi, my name's Kevin Grayson from Siemens Digital Industry Software, and I'll be hosting this session on Solid Edge model-based definition. Over the next 25 minutes or so, I'm going to show you how technology built inside of Solid Edge allows you to capture 3D design information and quickly push that information downstream without the need for creating that same redundant information in drawings, for example. This product manufacturing information can be easily leveraged from within natively designed Solid Edge data or from data coming from outside modeling sources. I'll show you how this information can be encompassed in easily readable model views and then pushed out to non-CAD consumers in widely used formats such as 3D PDF or HTML so that everyone has easy access to the data they need. One of the keys to eliminating redundant engineering information is to capture and retain it through the use of model-based definition. Since product teams can capture and share the engineering requirements, such as geometric dimensioning and tolerancing, materials, and assembly level bill of materials within the 3D model, the need for creating the 2D drawings is eliminated and it ensures that the final product complies with its engineering specifications. Let's take a closer look at how Solid Edge incorporates product manufacturing information. The execution of applying PMI to Solid Edge models is relatively seamless. Here are just a few examples of capturing important product information on both a single component as well as at the assembly level. Besides consuming this information within the CAD software itself, this information can also be conveyed to and read by Solid Edge manufacturing software, ensuring the parts are manufactured to the correct specifications. Other options to export PMI with the CAD model include JT and STEP AP242. In a few moments, we will demonstrate some ways that this information can be captured automatically during the design modeling phase. When leveraging proprietary synchronous technology in Solid Edge, PMI information is not only used to enhance or simply label the 3D model, but to create and drive it as well. This enables designers to actually create the model more in line with how the part will be manufactured versus traditional history-based approaches. As a result, this saves a significant amount of time, precluding the need to create additional PMI documentation. Let's take a look at this in action. In this demonstration, we're going to walk through a few steps a design engineer may go through to leverage synchronous technology to capture critical product information. We're going to use a design approach called top-down design, where we will design the upper yoke for the front forks in the context of the motorcycle assembly. Designing the parts in the context of other parts guarantees fit and position and avoids interference problems earlier in the design process. Synchronous technology takes advantage of the closed areas of the sketch and creates regions that we can use to drag and create a 3D part. Transforming the sketch to 3D is a matter of dragging the handle. An important part of this process is that 2D sketch dimensions are automatically transferred to the 3D model and become manufacturing dimensions the shop floor most cares about. In the Pathfinder on the left-hand side of the screen is a node that captures all of the PMI information from the design. In addition, notice that PMI has adaptive view, meaning regardless of the orientation of the model on screen, the PMI information is always readable. As we change a PMI dimension, notice Solid Edge intelligently maintains the symmetry within the model and modifies the corresponding hole on the other side. Most 3D CAD systems require you to carefully plan the design steps so that edits can be made later. Using synchronous technology, we can create geometry in the most convenient manner, but have total flexibility in altering the intent later. 3D driving dimensions can be added at any time to simply edit or lock a design feature into shape. Again, notice the PMI drives the model and gives the designer the flexibility to specify exactly how the change will be made, something sketch dimensions don't allow for. As you can see, leveraging synchronous technology allows us to speed up the process of design creativity while making sure our designs are model-based definition ready from the start. As we just saw, synchronous technology has many benefits, including being ready for model-based definition. However, not everyone has adopted this method of design and design modification. That's okay. Solid Edge, since its inception, and even today, supports history-based modeling. This method of design utilizes an approach where much of the intelligence, including the dimensional information, is encompassed in underlying 2D sketches. While this design approach isn't as direct as synchronous technology, Solid Edge provides a way for us to easily transfer the 2D sketch intelligence easily into 3D PMI information. Let's take a look. In our motorcycle assembly is a component that was designed using this history-based approach. We'll open it to take a closer look at its detail. One of the caveats to making design changes to history or ordered-based models is understanding how it was designed in the first place. In this example, we're selecting the first feature, Protrusion 1, and editing its definition. Here you can see the 2D sketch, its dimensions, and other features to make modifications. This can be repeated for any of the defined features. Since ordered models do not use 3D PMI to create and drive the model, we could manually add this information using the tools found in our PMI toolbox. However, to save time, we can also utilize the information that has already been input into the model and copy that automatically to 3D PMI. In this example, we want to copy specific dimensions from our first feature. Simply select the desired dimensions and Solid Edge will copy those for use in model-based definition. Just as we saw earlier, those are captured in the Pathfinder for display at any time. As opposed to manually selecting individual dimensions, we could also window select all of them to speed up the process. Just as in synchronous technology, the copied PMI has adaptive view and is always readable on screen. What about data that wasn't authored natively within Solid Edge? Many companies either receive 2D or 3D data from outside their organization or have legacy data that was created in another CAD software. The data migration tools in Solid Edge allow for users to migrate both 3D models and their corresponding 2D drawings from several different CAD systems and still maintain the connectivity between the two. This in and of itself is a fantastic benefit for companies who choose to continue with traditional engineering and manufacturing documentation. For those companies who want to instill model-based definition, Solid Edge also provides a way to connect the manufacturing information from the 2D drawing directly to the 3D model, which automates the 3D PMI process. Let's check out how to use data from the other CAD software to quickly expedite the use of model-based definition. In this demonstration, we're going to take the manufacturing information from a 2D drawing and automate the process of connecting it to its corresponding 3D model as 3D PMI. You'll notice in the standard file open menu for Solid Edge the many different file types we can read in from other CAD software. First, we'll open the 2D drawing, which contains all of the manufacturing detail. One thing to take note of is the scale of the drawing. This will be important when making the connection to the 3D model later. Many 2D drawing applications utilize a layer structure that allows for the user to more easily display the information they want shown. Solid Edge can recognize these layers and replicate the ability to show or hide specific information on the drawing. With a single mouse click, we will activate a handy tool that allows us to either create a 3D model from scratch using the information on the drawing, or, in this case, connect it to our already existing 3D model that we directly opened from the alternative CAD software. Options for projection angle and which dimensions to include are also available. As we select the desired information, Solid Edge will automatically copy and paste the selected information into the associated 3D model. As we rotate the model to several common views, notice how the drawing views and dimensions are automatically aligned. Again, with a single mouse click, the 2D dimensions that were copied from the drawing automatically attach and connect themselves to their corresponding 3D geometry. We now have a complete parametric 3D model that can be driven with PMI. This ability to bring in data that was not authored in Solid Edge and make it intelligent without having to do tedious, history-based feature recognition is a huge benefit and allows Solid Edge users to use data from any source and be ready quickly for model-based definition. So far in our discussion of capturing PMI, our focus has been on capturing dimensional information. However, we know model-based definition is more than just dimensions. It also includes other factors in geometric dimensioning and tolerancing, as well as callouts and other design information. One thing to note about imported data is that it doesn't come into Solid Edge automatically with intelligent features. This can be seen in the Pathfinder. If certain information, such as hole callouts, need to be displayed for model-based definition and be accurate, this information needs to reside in the 3D model. Notice here how Solid Edge has the ability to recognize various features in imported data, including holes. As we activate this option, Solid Edge recognizes the type and parameters of every hole in the model. Now in our Pathfinder, we have actual features that can be referenced at any time and easily edited if necessary. The next step is to graphically call out the holes. This callout associatively maintains the hole feature even as modifications to the hole parameters are made. Here we'll make a quick adjustment to the diameter and depth parameters and watch as the callout automatically updates. As we mentioned at the start of this demonstration, model-based definition also includes other types of information. First, let's quickly display a section view. Solid Edge supports the ability to place model-based definition information in different display states. Various types of annotations can be placed in addition to what's been seen so far. In the feature control frame, we can add various symbols to define material conditions and tolerancing information. After something has been defined once, it can be saved for reuse later. Here, we'll place a couple of feature control frames and a datum on the section view of the 3D model. These are placed easily with a simple click on the edge or face of the intended target. Let's show a more detailed model-based definition with various dimensions, annotations, and callouts. Another nice benefit is seeing the cross-reference to the geometry highlighting whenever an item with model-based definition is selected on screen. Now that we've shown how we can capture PMI dimensions and other annotations, how can we break this information down into bite-sized, more easily readable chunks that can be understood and digested more easily? Model views can be thought of as advanced display configurations. Not only do model views specify which parts are visible, they also control the view orientation and which PMI dimensions and annotations are shown at any time. Various model views can be captured and stored in the Pathfinder, allowing for common tasks such as design reviews to be easily executed. In this next demonstration, we'll show an example of creating a model view showing various PMI information on an assembly and how we can toggle the display of several model views to review different states of our design process. Over in the Pathfinder, you can see the model views that have been created so far. Simply clicking on the view gives us access to apply it to see which information is contained within. Notice with each applied view, the information and orientation dynamically update. Also available is a review mode, which gives single-click access to toggle between each view. Let's start with a blank slate and walk through the steps to show how easy it is to complete the process. First, let's only show the components within the stationary block assembly that we want to focus on. Next, we'll orient the model that will allow us to convey the information in an easily readable display. We'll place a few PMI dimensions, locating a few holes followed by some other critical dimensions on the main block. We also have the ability to leverage property information by extracting part names or any other information specific to any part within the assembly. Other information like weld callouts can also be intelligently extracted. With some final adjustments to fine-tune the model orientation and final display, the last step is to create the view. We simply click on the View command, give it a unique name, and specify our desired settings. Now we have access to it along with all the other model views. We've gone through all the steps in Solid Edge to digitally alter the definition of parts and assemblies using our 3D models. How do we now convey this information from engineering to manufacturing or from manufacturer to supplier without requiring them to use the same CAD software? This is where Solid Edge MBD comes in. Solid Edge MBD is a set of tools that allows us to take the information we've created within our model views and publish that content to widely accessible and widely used formats such as 3D PDF, and HTML. In addition to conveying the solid edge data, other user-defined attachments, such as Word, Excel, and PDF, among others, can be added to create a technical data package. One of the tools that makes sharing this information possible is the Solid Edge MBD template editor. This template editor uses the familiar Solid Edge drafting interface to define a configurable template layout. Templates can contain interactive views of the 3D model, a view carousel for ease of transition to model views, bill of material tables, and other customer-specific information. Once the templates are ready for use, publishing the content to 3D PDF or HTML is a breeze. Options when publishing include adding attachments and generating neutral JT and/or STEP AP242 files, which have the ability to contain the PMI information and be read into various other CAD software and other applications. This allows for manufacturers to send data to downstream suppliers without sending entire proprietary CAD files or forcing suppliers to maintain matching CAD software to read files. If security is critical, a password protection protocol can be enabled, ensuring only those who are intended to consume the data have the ability to open the files. Within the Solid Edge interface inside the PMI tab, you'll notice both the template editor and the publishing tool. Selecting the template editor will take us into the familiar Solid Edge drafting environment. All of the familiar drawing and sheet setup tools are available for easy template creation. Oftentimes, companies want non-editable, inaccessible items placed on a background sheet. This option is available here as well. The first thing we will place on our template is a company logo or image. Just as in a standard drawing template, these images can be easily inserted and sized to fit the desired area. As we decide how to format the template with both viewing areas and other relevant information, you'll notice the added tools Solid Edge MBD offers. We'll start by adding the 3D view, which allows for direct interaction of the model views. A simple drag of the view allows us to size appropriately for our template. The view carousel, BOM table, and fields for user-defined PDF text can be placed and adjusted just as easily. For purposes of time, let's open a more detailed template that contains additional information. You'll notice options can be created for both assembly as well as part-specific templates. In this specific template, we have multiple pages which also contain links to property information. As models get published, their property information, such as part numbers, materials, surface finish, etc., can automatically be extracted to the 3D PDF. Like the template editor, the publishing tool is available from within the Solid Edge interface. Simply specify a name and location to save the document and finish by selecting any of the available options. In our example, we will attach a Word document along with a PDF to include within the data package. From there, select the Publish option and your 3D PDF is on its way. As we navigate the Publish 3D PDF, a single click on a labeled model view within the carousel makes available all of the information contained therein. Notice consumers can still rotate, pan, and zoom within the window interactively. Also notice a part selected within the BOM table automatically highlights within the view. Here we're transitioning over to the HTML version. As with the 3D PDF, this document is fully interactive. Other options include dynamic sectioning and interactive exploded views.